Okay, so chapter 13.2 is about the specific solution process and how solutions are made. So we have factors that affect the rate of dissolution, and dissolution basically means the rate at which a solute dissolves in a solvent. So the first thing that can affect the rate of dissolution is increasing the surface area of the solute. So if you take a sugar cube versus grinding or chopping or whatever to make it a powder of sugar, this is going to expose more of the solute to solvent. So you're increasing the surface area, and there's more contact between the solute and solvent. So more surface area means a better dissolving rate. So that's one thing you can do. Also, just agitating the solution. So obviously, the more things you do, the better the dissolution rate is going to be. But you could also just have coarse salt versus fine salt. So we haven't affected the surface area, but we are going to agitate it. That does also help the rate of dissolution because you're bringing more solute into fresh solvent that doesn't have anything dissolved in it yet. You're basically, once again, increasing the contact. Now, if you grind it up into a powder and agitate, that's an even better way to increase the rate of dissolution. You could also increase the temperature of the solvent. And remember, solute's what's being dissolved. Solvent is the dissolving. So in our case, it's usually solute is a solid, solvent is a liquid. But as you saw in the last section, different types of heterogeneous and homogeneous mixtures, you could also have a liquid in a liquid or whatever state of matter to make a solution. So increasing the temperature of the solvent is basically going to increase the kinetic energy of that solvent's molecules. And the faster that the molecules move, the more collisions are happening. So once again, you get more solute exposed to solvent. There's these pockets that open up because the molecules are farther apart as they're heated, and that allows more contact. So what is solubility? Solubility is basically the amount of substance that's required to form a saturated solution with a specific amount of solvent at a specific temperature. And soluble is basically just how capable is something of being dissolved. So in chapter 14, we talk about insoluble versus soluble. So soluble meaning how capable it is of being dissolved, and insoluble how incapable it is of being dissolved. So an unsaturated solution basically means, if you look at this picture, there's less solute represented in green than what can be dissolved. We could add more solute and it could be dissolved. But also, we just said, we can add more solute, but at what point can we not add any more? Where there's 2 points where you have a volume of solvent that cannot dissolve any more solute. So 2 possibilities. The first possibility is called a saturated solution. So once again, green for solute, blue for solvent. This is basically when you have the maximum amount of solute that can be dissolved in this given volume at that temperature. We say this basically is at an equilibrium because you're not going to have anything else dissolving, but you're also not going to have anything crystallizing or falling out of solution. You could also have what we call a supersaturated solution. So this is going to contain more solute that can be dissolved. So think about if you put sugar in iced tea and you stir and stir and stir and it dissolves and you add more sugar, and then eventually the sugar just sits at the bottom even when you're stirring. That's a supersaturated solution. You can see that there's more solute in that glass than can be dissolved. You've tried to dissolve it. However, sometimes you can have a supersaturated solution that looks saturated, but it's actually supersaturated. And disturbing the solution will cause this recrystallization. So we basically say that it recrystallizes, it falls out of solution. So a quick video, I don't think there's any volume, that kind of shows you this super saturated solution that looks like everything's dissolved, but as soon as you agitate it or you add a seed crystal, which is just one more crystal of the solute, it shocks it into recrystallizing and all of that falls out of solution. So you can see the moment that they added that seed crystal, all the excess solute fell out. So it looks like it's freezing. It's not freezing, it's just recrystallizing and coming out of solution. So let's talk about solute and solvent interactions. So we like to say that likes dissolve likes. We don't get a lot into polarity, but basically this is a rule you can use to predict if one substance will dissolve in the other. So what is the like? The like can be the type of bonding, polar, nonpolar, covalent, ionic. It can just be the polarity of the molecules, polar versus nonpolar. And it can also be the intermolecular forces that are present between the solute and solvent. So this says, help, help, I'm dissolving. And the other bear says, but bears are not insoluble. Or bears are insoluble, meaning, oh, he's not going to dissolve. And this bear says, but that's easy for you to say, you're not polar, because it's a polar bear. So basically they're trying to make a pun that water's polar and the substance is supposed to be polar, so it will dissolve. So polarity, like dissolves like. Also, the phase of matter can sometimes help something dissolve, but not always. So I just said water is a polar molecule. You have this uneven distribution of charges, and that's what makes it polar. Okay, so what is hydration? Hydration, just as far as the concept, is when you have water as a solvent. Solvation is when you have anything but water as the solvent. So we can use hydration and solvation kind of hand in hand, except hydration is using water, solvation is not using water, any other liquid. So if we're dissolving an ionic compound in an aqueous solution, aqueous meaning water, for example, sodium chloride, NaCl, salt, table salt, and water. So this is what our sodium chloride looks like. Sodium is in the gray positive metal, and chlorine is the green negative nonmetal. They've bonded together. And then we have our water molecules. So basically what happens is you have these charge ends of the water molecule. So we have two positive hydrogen ends and one negative oxygen end. So those charge ends are going to attract the opposite charged ion from the ionic compound, because we know that ionic compounds do have charges. They're just kind of neutralized when they're holding together. But as soon as they break apart, you have ions. So what happens is the water surrounds the crystal of salt, and it pulls them apart based on attraction, and then the water surrounds that ion and keeps it separated. So we call this a sphere of hydration forming, or if you're not using water, a sphere of solvation. So you have this crystal of ion in the middle, in this case a positive sodium, and notice it's surrounded by the negative oxygen sides of the water. If this was the negative chlorine, it would be right here, and then water would be surrounding it this way, except now you would have the negative or the positive sides of the water, hydrogen, attracting to the negative chlorine. So sphere of hydration is when you have water doing this. Sphere of solvation is just when you have anything else besides water. So once you have the sphere of hydration or solvation, we can say that the ion is hydrated because it's surrounded on all ends by water. Or if it's not water, we say it's solvated. So now that every ion is separated, it can diffuse into solution, goes between pockets of water, and then more ions are exposed, and the process just repeats. And that's how you get this dissolving process to happen. So it's exposing and hydrating, exposing and hydrating. But you do need enough solvent to keep this process going, or you're going to have a supersaturated solution. So if you still have waters left over that could hydrate, that's an unsaturated. If you have just enough water, that's a saturated. But if you have more ions than what you have water, it's supersaturated. And that's why those crystals fall out, because they're not hydrated. They're not actually dissolved. Okay, so we talked about how you can increase temperature to help the dissolving process, dissociation or dissolution. What's the actual temperature effect on solubility? So if you consider a gas-liquid situation, if you increase the temperature of the gas, you're going to decrease solubility. So think of it this way. Here's our liquid in blue, and here's our gaseous molecules in like light purple. If you increase the temperature of a gas-liquid solution, meaning both phases of matter are present, you're going to make the gas molecules move faster and faster apart to the vapor phase. That's going to decrease solubility. We want to dissolve them in the liquid. Well, if they're bouncing around above us going to the vapor phase, they're not going to dissolve. Obviously, the opposite, if you lower the temperature, because you're slowing down the gas particles, and therefore they are able to move into that liquid phase and dissolve. If you consider a solid liquid situation, which is what you're used to, for example, sugar and water, usually increasing the temperature of the system is going to help solubility, because you open the pockets up between the liquid particles and the solid can go inside and basically dissolve. But it does depend on your solute and solvent. It is situational. Most of the time this is true, but not always. So what about the effect of pressure on solubility? Okay, so effects of pressure on solubility. So changing the pressure can have little effect on the solubilities of solids and liquids, especially when you have a liquid solvent, but it will affect a gas-liquid solution. So you basically have to remember that pressure is not going to have a great effect on solids and liquids because their molecules are already close together. So pressurizing them doesn't do a lot. When you have a gas-liquid solution, you can really compress the gas particles, so it is going to have an effect. And this is called Henry's law. So Henry's law basically says increasing pressure increases solubility of a gas in a liquid when you're at constant temperature. But this really only applies to the gas-liquid solutions or situations or systems. So think about bottling pop, Coke, soda, whatever you call it. So we bottle Coke and other pops about 5 to 10 atmospheric pressure. And that's basically to force the carbon dioxide to enter the liquid phase, and then they seal it. So that's why when you open it, it fizzes, because you have some of that gas escaping because it's not pressurized in that container anymore. So effervescence is basically when you have this rapid escape of a gas from a liquid. So that's when you get this major fizzing, and sometimes you have a situation that looks like this, because they had to pressurize that gas to go into the liquid phase. As soon as you open that cap, you're releasing that pressure, and it's going to want to come out of the liquid. So if you increase the pressure on a gas-liquid solubility situation at a constant temperature, you're going to increase solubility. But obviously you should know that warmer situations cause Coke to go flat. And that's because it's warmer, the gas particles aren't as close together, they will escape more into the vapor phase. Okay, so heats of solution. Basically, it's the formation of solutions, the result in the change of heat energy. So you're going to have heat either being absorbed as a positive change or released as a negative change by the system. So heat of solution is defined as the difference between the heat of solution and the heat of the individual parts within the solution, the solute and solvent. So the amount of heat that's absorbed or released as the solution forms, we can figure out. And the unit's going to be kilocalorie per mole. So kcal for kilocalorie over mole for mole. You also just need to remember exothermic versus endothermic. So exothermic is when your heat energy is given off to the system, exo meaning outside. So it's going to feel warm to you because the heat is leaving the system and going into the environment. You can also have endothermic, which is when endo meaning inside, heat energy is being absorbed into the system. It feels cool to you because it's stealing the heat from the environment and putting it into the system. So when you have a solid dissolved in a liquid, this is kind of like the graph. It looks something like this. So 3 steps. The first step, you're basically having the solute particles becoming separated from the solid. Energy is being absorbed. So we have the solid breaking apart into the solvent. Step 2 is when you have solvent particles being moved apart to allow, solvent particles are moving apart to allow the solute particles to enter the liquid and be dissolved. We also have energy being absorbed, so another up arrow. And then step 3, in this case, a solvent is being attracted to the solute, and you have that solvation, sphere of solvation or sphere of hydration forming. In this case, we have energy being released, so a down arrow. So basically, you find the heat of solution as what's the difference between this line and then this line. So what's the up versus the down? In this case, we know it's exothermic. Okay, so just once again, example of an exothermic heat of solution. So in step 1, solute particles are becoming separated from the solid chunk, the solid mass. So we have an upward arrow, heat is being absorbed, endothermic, positive change, up arrow. And then in step 2, we have the solvent particles are doing that sphere of solvation. They're allowing more things to move apart. There's more solute entering the liquid and being dissolved. It's also an upward arrow, so it's once again energy being absorbed, endothermic, a positive change. But then in the third step, you have the solvent particles attracting and surrounding the solute particles. Now you have energy being released from the system, so exothermic, and it's a negative change, so the decrease. Okay, so here's how you tell if a heat of solution is exothermic or endothermic. If the heat of solution is negative, you have heat being released, it's exothermic. So basically the arrows from step 1 and 2 are less than the arrows from step 3. So for example, right here, upward arrow is smaller than the downward arrow, exothermic. You have more energy being released than taken in. Same thing here. Upward arrow in size is smaller than the big downward arrow, exothermic. You have heat energy being released in general. So it's like saying 5 minus, or 10 plus negative 12 equals negative 2. Okay, so you're having something left over. If you have a heat of solution that's positive, you have heat being absorbed, it's endothermic. So if step 1 and 2 is greater than step 3, you've got an endothermic solution, you have something being dissolved. So if it looks like this, the upward arrows are greater than the downward arrow, you have this excess positivity, it's endothermic, it's absorbing into the system. Okay, so that is part 2 of chapter 13.